Now, good morning, everybody. Somebody asked me if it is possible for. Now, I've already sent you the regulation for online exam, online midterm exam yesterday. Okay, please make sure you have received the notification because you have to observe the regulations very carefully in order to attend exam. So please make sure that you read the document, and you should know the class, the Zoom class that you are assigned to, and attend that class specifically during the exam. So if you we also have upload the documents to the Blackboard, so you can also read it in the Blackboard. Now, somebody asked me if it's possible for a local student to attend face-to-face examination. I would say yes. You will be eligible for attending face-to-face examination if you feel that more comfortable. But I have to reserve a separate room for that. And I have to find some TA to invigilate that exam. So please make sure that you have that needs. If you cannot attend, if you cannot have a stable internet connection, or you have other problems with your home, or you cannot find a suitable place for doing the exam, then you're eligible to apply for that. And if you want to apply for that, please send me an email explaining why you would like to attend the face-to-face exam. Now, I know that some of your Chinese name is written not correctly. I cannot correct it because it is actually from the PHYS, and I don't know why when I download the file, there are some problems with the Chinese characters, and so your Chinese name may be written incorrectly. But that is not a problem. We always refer to your English name, so that's not a problem. But I'm sorry to let you know that I will not be able to correct it for all. Okay. Now, so if you really want to sit for a face-to-face exam, you please let me know at least 4 working days before the exam. Okay. So the exam will be held on 11th of March. Okay. So please attend it punctually. You have to attend it 15 minutes earlier. So the exam actually starts at 2:30, but the TA has to check your working posture and to check your student ID, etc. So it will take some time. So you have to enter the Zoom session at 2:15. Okay, so you ended at 2:15 and you started doing the exam at 2:30. Okay, and you are not allowed to leave early. You have to stay until the end of the exam. After you submit all the students submit the answer, and the TA tells you that you can leave now. Now, for those who have special needs, I will inform you separately, but I need some time to prepare for that. Okay, so I would have a separate communication with you if you have a special needs in your examination. Okay. All right. Then we continue with our lecture. Now, in our PHYS lecture, we already have discussed about the concept of center of mass, right? And we have proven that, we actually have proven that if the center of mass is defined by this equation, okay, summation MIRI divided by total mass, we divide the whole object into many small pieces, and for each pieces, the position vector is Ri. So we form a summation of the mass, the product of the mass with the position vector, and we divide it by the total mass, we get the position of the center of mass. So the whole body, it seems to be, has a weight that concentrates at the position of the center of mass. That is the concept, okay? And if we define the center of mass position like this, then we find that the center of mass position will obey the Newton's second law, just like the ordinary form of Newton's second law for a single particle. It just behaves like a single particle. Okay, but of course, the mass is now the total mass of the system, and R stands for the center of mass position. So this is an acceleration of the center of mass, not the individual point mass, but the center of mass acceleration as a whole. Okay. Now, so the important implication is that the center of mass behave like a single particle. Like, for example, if I throw a hammer in the sky to the sky, then the whole hammer may rotate in a very complicated way that I cannot describe easily. But as long as I trace the position of the center of mass, I will find that it just follows a simple projectile motion, just like a point mass that obeys the same motion. Okay, so that is the mysterious thing. Okay, so it's quite interesting to notice that. Now, the MIT University, they have a very interesting demonstration on this properties. Now, they use an external object and they locate the position of the center of mass of that object by using an LED. So they put LED at the position of center of mass, and they turn off the light, and they throw that object, and you can see that that point light, that center of mass position, will follow a simple projectile motion. Okay. Now, and when they put the position of the LED at another position, but not at the center of mass, they actually have a non-uniform disk. For non-uniform disk, the center of mass position is actually not at the center. So if you put the LED at the center, which is not the position of the center of mass, and you throw the object, you will see the LED light jiggling around, not following a simple projectile motion, and that is the important difference. Now we'd like to see the video now. All right, this is the video. Now, this is the position of the center of mass. Now, you can't notice anything special when the light is on, but as long as you turn off the light, then the things become very apparent. Now, you see, just a simple projectile motion. You can't distinguish whether it's this extended object or not. Now, but for this object, is not at the position of the, this is also a center of mass position. But for this object, the center of the object is not the position of the center of mass because it's a non-uniform disk. Now you see the jiggling of the center of mass, of the position of the center position. Now let's see it again. This is at the center of mass position, okay? But for this object, the center of the object is not the center of mass. So you will see that it does not follow a simple projectile motion. Okay. Now here we throw the object again, but at the position of the center of mass. So you see the difference. Okay. Now, so this is the way for us to calculate the position of the center of mass. We just follow this formula, okay? And since this is a vector equation, we can decompose it into three scalar equations. The Ri has the component xi, yi, and zi. So the equation for xi, y, and zi, they give respectively the three coordinates of the center of mass, x, y, and z coordinates, which are denoted by big X big Y and big Z. Okay. Now there are a lot of interesting phenomena that show the importance of the center of mass. For example, I don't know if you have played the mobile phone game called Angry Birds. If you are old enough, then you have played that before. And in the Angry Bird game, the birds simply follow the projectile motion. But sometimes the birds will explode, right? Will expose into 3 pieces. And during the explosion, you find that the center of mass position is in the middle bird. Okay, so if you trace the position of the middle bird, is also follows a simple projectile motion. That is the position of the center of mass of the system. So in design the video game, you have to obey some physics as well. Okay, you have to locate the center of mass and you trace the center of mass position as the simple projectile motion. Okay. Now, for example, if you have ever seen a firework, you see after the firework explode in air, you can still trace the center of that firework, and you will see the whole firework, the center of the whole firework will fall, just like a projectile motion. Of course, with some air resistance, but essentially that is the projectile motion trajectory. Now, Sirius 天狼星 is a binary star system. 天狼星. A binary star system consists of 2 stars. Sirius A is a giant star, and Sirius B is a white dwarf, and they revolve around their common center of mass. Okay, so their center of mass is moving relative to the Earth. Okay, so as a whole, you can see this motion. Okay, the 2 stars revolving around each other, while the common center of mass is moving relative to the center of to the Earth. So you see the center of mass move in a almost straight line, right? This is the position of the center of mass. It moves almost in a straight line in the sky. So these are the years from 1910 to 1990. So you can see the center of mass move almost in a straight line across the sky. And the 2 stars revolve around that center. Okay. So it's important to let you know that even though for this system, which is not a rigid body. Now, a rigid body means a body that cannot be deformed, that cannot be separated into pieces. That means a rigid body. For example, this is a rigid body. It is solid. It cannot be deformed. It has a certain shape which is fixed. That is called a rigid body. Now, this is not a rigid body. This book can be deformed, right? This is not a rigid body. And of course, some of this soft thing is not a rigid body because we cannot deform it. And for those things which can be separated into pieces, they are also not a rigid body. And it is important to notice that the concept of center of mass hold not only for rigid body. You can see none of this situation are a rigid body. Okay, the Angry Bird, when it's exploded into 3 pieces, of course it's not rigid body. Firework is not, of course not, but they still obey that equation. Okay, this equation. If you trace the position of the center of mass, then it behaves like a single particle. Okay, so that is why it's so important in physics to know about the center of mass. Now let's us have more intuitive understanding of that equation. Okay, that equation of the center of mass. So for example, if you have 2 masses now, 3 kg and 5 kg, they are respectively located at x equal to 2 and x equal to 6. Now this is a one-dimensional problem. You know that the center of mass must be somewhere along the line joining the 2 masses. Okay, that is a one-dimensional problem. That the only variable is x. So now I calculate the position of the center of mass. I first have the mass itself, which is 3 kg, multiplied by the coordinates. So 3 times 2 plus 5 times 6, and divided by the total mass of the system, and that is 3 plus 5. So after some calculation, I find that this is 4.5. So you see the center of mass is closer to the massive object, to the more massive object. So it's closer to the 5 kg mass than the 3 kg mass in this case. Because the center of mass concept is a weight mean. So if you have a higher weight, if you have a larger mass, then you have a high weight, and you draw the center of mass closer to you. Okay, so that is why the center of mass position is closer to the 5 kg object in this situation. Now we have a simple analogy of the center of mass thing. Now you might have learned a statistic before in your high school physics, right? In your high school physics, you learn how to calculate the mean or the average of a distribution. Suppose now you have 30 students and they have different heights. And essentially we divide the student into, for simplicity, we divide them into several categories, several height range. So you have the 10 student with a height of 160 cm, and 2 students with a height of 165, and 18 students have a height of 170. So how do you calculate the mean of this distribution? Now the easiest way, the brute force way, is to find the sum of all the heights of the student and divided by 30, right? Because we have 30 students. So we got 10 of 160, we got 2 of 165, and 18 of 170. We add them up to all together, and then we divide by 30. That is the way to find the average, right? But there's a careful way to do it. Instead of writing them all out and doing the sum of all this term, we use the frequency. Because the 160 appears 10 times, so that is equivalent to multiplying 160 by 10. And similarly, we have 165 appear 2 times, so we multiply 165 by 2, and then we multiply 170 by 18. So this is just the same as this, right? And we divide by the sum of the frequency in each category. The sum of the frequency, we have 10 plus 2 plus 18. So the total frequency is of course 30 students, is of course the total number of students. So we can rewrite the formula like this. Okay, and you can see if I turn the proofing, if I turn the frequency into m, okay, and I turn the heights of the student into the red thing, into the length, the coordinates, x coordinates, I find that this equation is in fact identical to the equation of center of mass. Okay, so you actually when you find the center of mass, you actually is finding the mean distance, but the mean distance is weighted by the mass that is present in the system. If you got a higher weights, larger weights, then you got more weights in the average. Okay, so that is the idea. Okay, so the center of mass concept is actually a weight average of the distance. Okay. Now here we have a 2-dimensional example. So we want to separately calculate the x coordinate and the y coordinates of the center of mass. So we have 3 masses at the 2 masses on the x-axis and 1 masses on the y-axis. And so we expect the center of mass positions to be somewhere here. Okay, so we form a summation of MIXI. Now the first mass is, I call this first mass, is 5 kg. It has a 0 in the x-coordinate. The x-coordinate is 0. So 5 times 0, the second mass is 4 kg. It has 1 as x-coordinate, so 4 times 1. This mass has x-coordinate -1, so 3 times -1. We add them up all together, and we divide it by the total mass of the system, which is 5 plus 3 plus 4. And so that's 12. And eventually, after doing this calculation, we find that the x-coordinate to be 1/12. And similarly, we do it for the y coordinates. For this mass, 5 times the y coordinate is square root 3. For this mass, the y coordinate is 0, so 4 times 0. Again, this mass, the y coordinate is 0, so 3 times 0. So the last 2 terms do not contribute. And we only have this term. And the total mass is still 12. So we now have 5 square root 3 over 12. So the calculation shows that the center mass is somewhere here. Okay, and of course, this system is not symmetrical with respect to the y coordinate, because the 4 kg mass on the right hand side is larger than the 3 kg mass on the left. So the center mass is closer to the 4 kg mass, which has a positive x value. Okay. Now the previous example are rather simple because they consist of discrete point mass. Okay, so you are given the position of the discrete point mass system. You just form the sum, average mean of that position. Now, but most of the system we encounter in our daily life is not consisting of discrete point mass, or the discrete point mass the number are so large that you cannot handle it. For example, atom, the number of atoms is so large, so you cannot count that point by point. Instead, we describe the object as a continuous distribution, and that is characterized by a certain volume and a certain density. So how do we calculate the center of mass position for a continuous system? That is the problem that we encounter. Okay. Now, in a continuous limit, when the summation becomes continuous, it becomes an integration. So naturally, we will expect that we have to use an integration to find the center of mass position for a continuous distribution. But how do we do that? Now, for simplicity, we confine ourselves to a 2-dimensional problem, which is a lamina. A lamina means a sheet without any thickness. We imagine now we have a sheet of material with a very small thickness. So the sheet is now lying on XY plane. And now we divide the sheet into a lot of small pieces. And for each of these pieces, we call the mass of the I pieces delta mi. Okay, so the I is a label. I may run from 1, 2, 3, 4, 5, 6 up to n. We divide the sheet into n small pieces. So for the I mass, we have for the I pieces, we have the mass delta mi, and the position of the I mass is characterized by this position vector ri, and ri has an x component xi and a y component yi. Okay. Now, so let us turn this into an integral. How do we do that? Well, we form a summation as before, because we can apply the formula for the discrete system, because we now divide it into discrete pieces. So we use the formula for the discrete sum. And that sum is the mass of the I piece, that is delta mi, multiplied by its position vector, that is ri, and we sum over all the I. Okay, so we sum over all the I means we sum over all the pieces in this lamina. Okay, and we divide by the total mass m of the lamina. So that is the summation formula that we learned in our discussion, right? Now, but in the limit where delta m tends to 0, when delta m becoming very small, when we divide the sheet, the lamina, into many small pieces, and each of these pieces is very small, the delta m become the dm, the differential in the integral. And this vector r, which is the position vector of the I pieces, now become the integrand. So we have the summation delta m ri becomes an integral of r dm. Does it make sense? Now, if we extract the x component and the y component, if we want to find the x component of the vector r, that is big X, we simply extract the X component of this position vector R in the integral, and it becomes X. So the integral becomes XdM for the X coordinate. And for the Y coordinate, we extract the Y component here, and it becomes integrate Y dm, and that's give me the Y coordinates. Okay. Now you may wonder why it is RdM but not MdR. Now don't confuse the two. They are totally different things. It is integral RdM. The D goes with the M but not the R. Do you notice that? Okay, the D, the differential, comes from the D, the mass. Because now I'm dividing the mass, right? I'm dividing the laminar into many small pieces, and for each pieces I call that dm. And R is not does not involve the D. It is simply the position of that pieces. So the D comes with the mass, but not the R. And in the very limit of the summation, when the number of pieces is very large and each pieces is very small, then it becomes RdM, the integral of RdM. Okay. Now the conversion from the continuous from the discrete sum to a continuous integration seems to be quite straightforward, right? We simply let the limit delta m tends to 0 and it becomes RdM, integral RdM. But the problem is how do we evaluate this integral? That is a difficult thing. Okay. Now, so we illustrate to you with a few example, and we hope you will be able to do it yourself. Now we use this example to illustrate the idea. This is a semicircular laminar. It consists of half of a circle, and the laminar is uniform. Okay, and the laminar is without thickness, so the whole thing lies on the XY plane. Okay, and the flat side lies on the x-axis, and that is the object is now symmetrical with respect to the y-axis. So you might expect the center of mass is lying on the y-axis. But we simply do not know how high is the center of mass position. Okay, so that is the thing we want to find. Now we would like to evaluate this integral, right? But how do we do that? Now we first divide the whole laminar into many horizontal strips. We cut it along parallel to the x-axis, and we cut it to a lot of horizontal strip. And for each strip, for a particular strip like this, in red, the distance of the strip from the x-axis is y, and the thickness of this strip is dy. Can you see that? Now, why I cut it like this? Why don't I cut it vertically instead of horizontally? Now you can see this strip is actually made up of many point mass, right? It is not a point itself, but it's made up of a lot of point mass extending along in the direction of x-axis, right? Now, but for each of this point, they are almost at the same heights from the x-axis. So we know what this y is. This y is the height of this strip above the x-axis, and it is the same for all the masses inside this strip. So we have a well-defined y for this strip. So that's why we choose to cut it horizontally instead of vertically. If you cut it vertically, then I don't know what y we should use, right? Because along the vertical strip, along a strip that is parallel to the y-axis, each of the points have a different distance from the x-axis. So I don't know what y we should choose, right? But now for this horizontal strip, I only have a one y. The y is the height of the strip above the x-axis. Okay, so the y is now well defined. But what is the mass of this thing? We have dm here, so we need to calculate the mass associated with this horizontal strip. Now, since the laminar is a uniform one, the mass is uniformly distributed on the lamina. So we can divide the total mass of the lamina by the area to get the density. And the density is uniform, right? Now this is the area density, meaning that we are actually calculating the mass per unit area. Okay, we divide the mass by the area. The mass is m. The area of the semicircle is pi r squared over 2, right? The density is 2m over pi r squared. Now, how do we calculate the mass dm of the strip? Well, I can multiply the density with the area of the strip. The area is the area of the red thing, of the red part, right? How do we calculate the area? Well, it's not difficult. We know the thickness. The thickness is dy. And we multiply the thickness with the length of the strip, we get the area. But what is the length of the strip? Now, this is the radius of the circle r. And the height of the strip above the x-axis is y, right? So by Pythagoras theorem, this length, this is a right angle triangle. So by Pythagoras theorem, this length is square root r squared minus y squared. Okay, but this is half of the length of the strip. So we need to multiply by 2 to get the full length of the strip. The full length of the strip multiplied by the thickness will become the area. And the area multiplied by the density will give you the mass. So that is the idea. Now, but after you evaluate the area in terms of y, you find that everything is now expressed in terms of y. So you know how to do the integration, because there's simply an integration in over y. Okay. Now I put the density back, okay, into this expression, and after canceling some of the constant, I got this. Okay, I got this expression. So this is my expression for dm. Okay, my dm is now expressed solely as a function of y. So I put this back to this equation, and together with another y in the integrand, I got this formula. I got this equation. What are the limits of the integration? You consider this figure. Now I chop the semicircle into a lot of horizontal strip, and the strip build ups from the x-axis, which is y equal to 0, right? On the x-axis, y is equal to 0, up to what? This highest point. The highest point is y equal to r. So I sum up all the contribution from the strip, from x equal to 0 up to y equal to r, right? From y equal to 0 up to y equal to r. So I have the limits of y from 0 to r. And if I know how to evaluate this integral, I can find the position of the center of mass. Now, these are the constants, so I just put it out of the integral, and m can of course cancel, and I'm left with this integral. Now, this integral looks rather ugly, but actually you can easily evaluate it without much difficulty. Now, the difficult thing is with the square root. I cannot evaluate the integral with the y squared in the square root. So let us put a substitution. Let us it is not a ball. It is a lamina. It is not a ball at all. It is a sheet without thickness. Okay, the sheet lies on XY plane. Okay, it's not a ball. It's not a three-dimensional object. It's a ball only. It's a sheet only. Okay. Now, we make this substitution. U is equal to r squared minus y squared. So we differentiate both sides. Du is equal to minus 2y dy. Because we differentiate y squared, we get 2y dy, right? Now, so what are the limits? When y is 0, right? U is equal to big R squared. And when y is equal to r, then we have r squared minus r squared equals 0. So u is equal to 0. So this will be the limits. of the integral in U. So we put everything back to this equation. Okay. Now the y dy here becomes minus 1/2 du, right? Can you see that? Now we have y dy here. The y dy here become minus 1/2 multiplied by du. So we have du multiplied by minus 1/2, right? And the guy inside the bracket, inside the square root sign, become u. So we have square root u. So we have a very simple integral of integrating square root u with respect to u. And of course, that gives me u raises to the power 3/2 divided by 3/2. Because the integration rule tells me that I have to add 1 to the power. So u raised to the power 1/2 added 1 is u raised to the power 3/2 divided by 1/2 plus 1, 1/2 plus 1, and again that is 3/2. And I evaluate at the upper lower limit. The upper limit simply gives me 0. The lower limit gives me a minus r cube, because this takes a square root and cube again. So we keep r cube. But since it's a lower limit, we have a minus sign here. And the minus sign cancel with the minus sign in front. And eventually, after canceling some of the constant, we get the y position as 4r/3 pi. Okay. Now you should note that if you evaluate 4/3 pi, you will find that 4/3 pi is actually smaller than 1/2. Okay, so y is actually smaller than r/2. Now, do you know why? You look at this figure. Now, r is the radius of the circle, is that right? So r/2 will be somewhere here in the middle point, right? But you see, the distribution of mass is not totally symmetric, right? You have more masses at the base. You have more masses close to the x-axis because the base is wider, right? So you have your center of mass position to be closer to the x-axis than the point y equal to r. And that's why the center of mass position is below r/2, because it's closer to the x-axis where you have more masses there. Okay, so that's why you have this expression. Okay, but you can't find it unless you do the integration. That is the important thing. You have to learn calculus to do the integration in order to know the position precisely. You cannot escape from that. Okay. Now we will have another problem for you to do in your exercise, in your homework. The homework is that you are given a triangle. You are given a triangle, and you are now required to prove the center of mass position of that triangle is 1/3 of, as is a position 1/3 of its height. That is h/3. If the height is h, then 1/3 of the height is h/3 above the base. Okay, so you expect the level to be somewhere here, 1/3 of the height of the triangle. Now, if you have learned some trigonometry in high school, you will find that there's a point called centroid. Now we divide the side, each of this side, into half, and we draw a straight line from the vertex of the triangle to the middle point of the opposite side. And we find that these 3 lines meet at a point, and that point is called the centroid of the triangle. So that is the bisector of the opposite side. Okay, the 3 bisector of the opposite side, they meet at a point called centroid. And the centroid point, this point, has a special property that its height above any of this side is equal to 1/3 of the height of the triangle. Okay, so if the height is h above the base here, then the centroid position will be h/3 above the base. And similarly for the other 2 sides. And you are going to prove that. And of course, without loss of generosity, we can do it for only one side only. The other two sides is simply identical, so the proof is identical, so we don't need to do it again. So we need to evaluate this integral for a triangle with the base placed on the x-axis. So we assume the base is now placed on x-axis, and the base is b, and height of the triangle is h. Okay. So the density of the lamina will be the total mass divided by 1/2 the height multiplied by the base. So 1/2 HB. That is the density. Now we divide the triangle into horizontal strip because we want to find the height of the center of mass. So we divide it in horizontal strip, just like we did for the semicircular lamina. Okay. Now, but what is the length of the strip? That is quite a difficult problem, right? Now, but that's not that difficult. We look at a similar triangle. We simply look at the similar triangle. Now, this triangle and this triangle, they are similar, right? The two triangles are similar. So the length of the strip divided by the base, this triangle and this triangle are similar, divided by the base, which is b, is equal to what? It's equal to the height of this small triangle. But what is the height of this small triangle? Well, if this height is y, then the height of the small triangle is h minus y. Is that right? And the height of the large triangle is, of course, h, right? So L over B, this length over the base is equal to this height of the small triangle h minus y over the height of the large triangle, which is h. Okay, so we have this formula. And after you rearrange it, you will find that L is equal to 1 minus y over h b, which is the length of the strip. The length of the strip multiplied by the thickness will become the area. And when you have the area multiplied by density, you get the mass. So what you need to do is to substitute this dm into the equation and do the integration. And of course, you do the integration from y equal to 0 to y equal to h. And I will let you complete it in your homework. Okay. So after doing integration, you will find that the result is h over 3. Is that okay? Now, let's stop here for a moment. We have a break. Let's have a break for 10 minutes.